That'd be great. Hi, everyone. Aaron Smith and Nancy Bakeman here with EEBA. We're happy to welcome you to Module 3 of our series with Joe Nebbia from Newport Partners. If you just took Module 2 on window and insulation tables for Climate Zone 1 and 2, you can go ahead and skip to Module 5, which will be insulation installation requirements generally. Otherwise, for the rest of you, we are happy to welcome you to window and insulation tables in Climate Zones 3, 4, and 5. In our next session, we'll cover 6, 7, and 8. So you can select as you're coming through this training program, whatever modules meet the area that you are currently building or developing or living in. So Joe, we're happy to have you. Just a couple housekeeping things. For those joining us in the live stream today, we do have a Q&A section at the bottom of the screen. Enter your questions there. I'll present those questions to Joe throughout. If you want to interact with us in the chat function, I'll try to answer your questions there as well. So Joe, as always, we welcome you and we really look forward to this presentation on the updates in the residential energy code.
Thank you, Aaron and Nancy. It's always a pleasure to be here talking to EEBA and your partners. So we're going to get started today and talk about Climate Zones 4, 5, and 6. I'm sorry, 3, 4, and 5, excuse me. And if you're interested in other climate zones, join us tomorrow for 4, 5, and 6, or catch the recording. As Aaron mentioned, we'll also be doing other modules. They'll be coming up in January: insulation, installation, air sealing, ducts, heating and cooling, hot water and lighting. And then finally, we'll do a module on the different performance paths and how they work, and also the additional efficiency packages in Section 405 in the new 2021 IECC code. So I'm going to talk today about the IECC International Energy Conservation Code as it's published by the ICC. So your local code may be a little bit different. So please note that you might have amendments you need to pay attention to. If you have questions, please submit them through the chat. I don't mind stopping and answering them. We are going to take some quizzes. Don't worry, they're not graded, but it does help me to know how well I'm communicating some of this information. So if you're here with us today and you'd like to access and participate in those quizzes, if you have a QR reader on your code, you can actually scan the screen with your QR reader and access the quiz. If you want to do it now, it's great to get set up. This QR code will also come up when I get to the questions, but if you
Joe,
set it up now,
Joe,
you'll be ready.
For people watching this on the EEBA Academy, not live, they won't be able to use this, right?
That's correct. Yeah, this is only for the live audience today.
Okay. Thank you.
But you will hear the answers if you're listening to the recording. So use that QR code if you want to do it on your phone. If you just have your computer and want to go to a different window in your browser, you can go to this website, slido.com. You can't click on it because it's just on my PowerPoint there. It's not a live link, but type in slido.com and there's the code for you. So I'm going to give you just a moment to get yourself set up in the quiz. Again, as I get to these, the quiz will go live on your device if you're already logged in. You don't have to sign in or have a password. You're just accessing my quiz on there. So use a QR code or this website. And again, it will come up as the quiz goes forward. So I'll give you just a moment longer to get set up. Okay, so just real quick, we covered this in module 1, but I want to just give a real quick reminder because it's very relevant to what we'll talk about today for the Energy Code. The Energy Code has a number of requirements found in prescriptive tables. That's sort of if you're following the prescriptive path in the code, you're not doing an energy model. It gives you some targets for your insulation and window efficiency. And these targets are meant to try to control several different things. In general, the Energy Code is very concerned with controlling heat movement. That's one of the primary purposes of the Energy Code. It's to control heat movement. It's to keep the hot air in the winter and the hot air out in the summer, depending on your climate and all that sort of thing. And there are three primary ways the code controls heat movement. Conduction is one, and that's heat transferring across a surface via touch. So if I touch a hot stove, I'm being burned by conductive heat movement from the stove into my hand, right? If I've got, if I'm holding something that's cold, the heat from my body will want to go into that cold object, which is why it feels cold to me. Convective heat movement is heat moving in the air. That's controlled mostly by air sealing. So it's not in what we're doing today. And then finally, radiant heat movement, which is how the sun heats the earth, solar radiation. And also the code tries to control this primarily using solar heat gain coefficient measurement in windows to try to stop some of that radiant heat from entering the house, especially in the warmer climates where we don't want to have a lot of internal heat gain. So that's primarily what the code is trying to do when it's requiring insulation in windows of a certain efficiency level. So the concept for insulation is that we're primarily trying to control conduction. Some insulation does other things, right? So some insulation will also air seal. But when the code sets requirements in these tables we're going to talk about in a moment, it's trying to control conduction. So if it's cold outside and warm inside, so winter right now where we are, or fall or anything like that where it's going to be cold outside and warm inside, the heat wants to move from more to less. So the heat wants to go from inside, that heated air that we've paid money to heat, and it wants to go outside. And the insulation in our walls and the insulating windows and things like that are intended to prevent that heat from conducting across the building envelope and escaping to the outdoors. The code deals with this with a few different measurements. One is called R value, and that's resistivity to conductive heat flow. So R value is how well an insulating material can stop heat transfer across the building envelope by resisting conductive heat movement. Higher R value means it's more resistive to conductive heat movement. And the code, when it talks about R value, it's talking about labeled R value. And this is important when it comes to code compliance, because I often hear the term thrown around, effective R value. That's not what the code's talking about. So when the code says you have to have R38 in your attic, for example, that's an amount of insulation. If it's a bat of insulation, then it should be labeled on that bat of insulation. If it's a blown-in insulation or something like that, then the product should have specifications that say how much R value per inch there is. Now, how you install that insulation will have an effect on how well it performs, but the code is requiring a labeled amount of insulation or a tested amount of insulation if it's not physically labeled. So for example, if my insulation also air seals, I've heard some manufacturers or installers claim that this gives it a better effective R value, which is nonsense. It does not change the R value. It's a more efficient product because it does two things at once, but it doesn't raise the R value. So that's important from a code compliance point of view. U value is the inverse of that. It's conductivity. So it's how well something conducts heat across its surface. So in this case, because we want to stop heat movement, lower U value means it's lower conductivity or higher resistivity. When the code talks about U value, it's either talking about windows. So the window product has a rated U value or conductivity, and lower is better. Or it's talking about the assembly U value. And this is when you get a little bit into effective R value or effective conductivity, excuse me, because the U value for an assembly, a wall assembly, for example, takes into account everything like studs and stud spacing and framing factor and sheathing and things like that. And it builds up a U value for that assembly. So if somebody says, well, my wall has an effective R value of this because it's got a framing factor that's different than the code, they really need to be using U value in that case for compliance. Today, we're going to be talking entirely about prescriptive compliance in the code. So performance path and energy modeling doesn't play into this discussion. There are some modeling tools or some tools, calculating tools you can use for prescriptive compliance, but we're not going to be doing a whole building energy model for these concepts here. So within the prescriptive path, there are 3 different compliance options. We can do insulation R value, and again, that's labeled R value. Also, we could do assembly U value. Again, that's a whole wall or a whole attic, including framing and air films and paints and all that sort of stuff. And then finally, there's the whole building UA. And the whole building UA is a area weighted average calculation of the U value. So it takes my walls, my windows, my ceiling, my floors, my basement, whatever I'm insulating, and it does a whole building calculation of the U value times the area of those assemblies. And then I can use that method to gain a little bit of flexibility, and we'll go through an example of that in a little bit. So first, I'd like to talk about windows, and again, please stop me if you do have questions as we go. For Climate Zone 3, again, we're going to cover 3, 4, and 5 today, and all of these climate zones are split into A, B, and C. A being humid, B being dry, and C being marine. Most of the marine climates are all pretty much on the West Coast. The humid climates are on the East Coast, and the dry climates are in between, and some on the West Coast, and in the middle part of the country. So for Climate Zone 3, you can see here the purple highlights are where the code has gotten more stringent. So if you're in a jurisdiction with a 2009 IECC, you have a 0.50 U factor window or lower. Lower is better. That was the requirement a while ago. Not a lot of states are still on the 09, but some are. Skylight U factor of 0.65 and a solar heat gain coefficient. That's a measure of how much radiant heat we're blocking from passing over that window, is 0.3 or lower. There's also an air leakage target in the code. It's not actually in the tables, but I listed here because it's part of the window specs. That's a tested air leakage value of the window itself. It's not the blower door we're talking about for the whole building at this point. That's just the air leakage of the window unit. In 2012, windows got more stringent in Climate Zone 3. You can see we jumped all the way down to a 0.35 U factor. That's still a pretty common window today, and pretty easy to find. 0.55 U value for skylights. And the solar heat gain coefficient got more aggressive in Climate Zone 3 because more heat, as we move further south in the country, we want to stop the radiant heat from entering because those climates are cooling driven. There's more cooling going on. And so we don't want our interiors heating up because of the solar energy coming through our windows. We want to try to direct some of that energy away to prevent us from having to cool the space too much. No change in 2015 code. 2018 code, very small change from a 0.35 to a 0.32 U factor. Again, still a pretty common window, easy to find. And then 2021 code, we go all the way down to a 0.30. This is the same U factor required all the way to Climate Zone 8. So Climate Zone 3 to 8 now has a 0.30 U factor in the code. So keep that in mind. That until recently would have been like a Energy Star level window. So the windows have been progressing in a more efficient target in the code. Climate zones 4A and B, so that's the humid and the dry. The 4C is actually put in with Climate Zone 5 in the tables. So if you're in 4C in Washington, Oregon, California, you're going to be looking at the Climate Zone 5 tables. Again, kind of similar to Climate Zone 3, we saw some changes in stringency in 2012. 2018, we moved to a 0.32, just like Climate Zone 3, and 2021, we moved to a 0.30 U factor. So the conductivity is getting less in these windows as the code has has advanced. We have a 0.40 solar heat gain coefficient in Climate Zone 4 because we're okay with a little bit more solar heat gain than we are in Climate Zone 3. Climate Zone 5, again, some changes in stringency started in 2012, and then no change in 2015. 2018, we moved to a 0.30, and that's where it is again in 2021. So again, 0.30 U factor window is the highest U value you see in a code compliant window in most of the country now. 3 to 8 is that target. And then we have, for the first time in 2021, a 0.40 solar heat gain coefficient for windows. So 0.40 or lower. Prior to 2021, there was no requirement related to solar heat gain coefficient. In fact, there was some thought that maybe in Climate Zones 5 and up, solar heat gain might be good if you're doing passive solar design. The prescriptive path, again, there's other paths around this if you want to still do passive solar design with high solar heat gain, but the prescriptive path caps you at a 0.40 for that window now. The argument, at least, is that homes in Climate Zone 5 benefit from a lower solar heat gain coefficient overall. So that's something to keep in mind. If you're building in Climate Zone 5, you've got a new requirement there for the first time. And there were a number of climate counties in Climate Zone 6 that in 2021 moved to Climate Zone 5. So be sure to check your county if your jurisdiction adopts 2021 and you were in a 6, it might have moved. So that's important to check. Every window, if you want to know where to find these numbers and whether your window is compliant, every window should have a NFRC label on it. If it doesn't, it's not code compliant, and there's a penalty for that. It should have the U value, the solar heat gain coefficient, and the air leakage tested on every window that's in an IECC compliant home. If you don't have that sticker, you can see here on the right, you have to accept some default values. So for a double pane argon filled vinyl window, you would end up with a 0.55 U factor for that window as a default because you don't have any information from the NFRC sticker. So in this case, Climate Zone 5, 4, 3, 0.55 would be worse than the prescriptive target in each case. And you'd have to use another compliance tool to be able to use that window if you don't have the sticker. A couple things to remember though, there is some flexibility even in the prescriptive path. I'm going to talk more about the whole building UA, but in that case, you can use added insulation to trade off against windows. That's possible. You can also do an area weighted U value. So let's say you do have this window and it's a 0.55, but all the rest of your windows have stickers on them and they're all better than code. Well, you can do an area weighted average of your U value and still comply using the prescriptive tables. You can also do that with an area weighted average with solar heat gain coefficient. Maybe you want higher solar heat gain in some orientations, but not others on your house. And so you have better than code on some side of the house and higher solar heat gain on another side. And in that way, you could still do an area weighted average. There are also a window and door exemption up to 15 square feet for windows and 24 square feet for doors that you can just take out of the compliance according to code. So if you have some sort of strange decorative window, strange is probably the wrong word, a different unique decorative window that doesn't have a sticker, or you've just lost a sticker on one, as long as it's within that square footage, you could exempt that, that window from your compliance. So I'm going to start now with
Joe, just a quick
Yeah,
question. Is that window exemption for 15 total square feet of windows or yes, right?
yes,
Okay, that's what I thought.
15 total square feet.
Yeah.
So we're going to go on to our first quiz now. So if you've logged in ahead of time, this should be popping up on your device or on a different tab. If you use a different tab in your browser, you can go ahead and answer as soon as you want. I'll give you a few moments to answer since this is the first one. And the question is, in climate zone 4, a maximum solar heat gain coefficient of 0.40 is required to try to control what type of heat movement: convective heat movement, conductive heat movement, radiant heat movement, or inductive heat movement. And you can go ahead and answer now if you're participating live. Don't be shy now. This is a good indication of whether some of that information is getting across or not. So please do participate if you're on today. All right, we've got a couple of answers here, and I'll give it just a few moments longer. Again, it's not graded. You don't get credit. So feel free to take a shot.
Joe, maybe we should have had prizes for people.
Yeah, that's right. Maybe we should have graded it.
Yeah, that's right.
That's right.
I got
Okay.
100%. I think I got a 90% in the last one. So
Okay, well, hopefully you'll get 100% on this
I
one
should.
since it's a lot of the same content. So we'll go, okay, we're going to go ahead now. Radiant heat movement, that's correct. Solar heat gain coefficient is trying to stop radiant heat movement across the window. Next question, in climate zone 5, if I install a window with a 0.32 U factor instead of the required U of 0.30, that's in the 2021 code or 2018, that window could still comply using which compliance option listed here? There are other performance options, but out of the prescriptive compliance options, which option could be used? And actually, there are multiple correct answers on this one.
can you select multiples, Joe?
Yes, you should be
okay.
able to select
Okay,
multiple.
great.
Give it just a minute more here. Moment more, I mean. Okay. 15 square feet exemption, yes, as long as the window fits within that square footage. Whole building UA trade-off, yes. Area weighted U value calculation, yes. R value method, nobody got the wrong answers, so that's good. You can't, there's no R value method for windows, so that's positive. Okay, again, please stop me if you have questions. I'm going to move now from windows to insulation and talk a little bit about how those tables work and what to look for there. So for climate zone 3, if you're building in that part of the country, there's been some changes. 2009 to 2012, there was some added stringency, and now in 2021, we see another jump in stringency. There was no change in insulation requirements in the R value tables from 2012 through 2018. I'm going to talk a little bit as we look at these about what these different measurements mean. So for the ceiling R value, that's an amount of insulation. That's pretty easy. And in 2021, we're at an R49 in climate zone 3. So that's a change in stringency. For wood framed wall R value, there's a 20 plus 5, a 13 plus 10, or a 0 plus 15 option. So even though all of these are in the prescriptive tables, there's still some options as far as what you can do if you're going to use these tables. So 20 plus 5 in this case means R20 in the cavity, the wall cavity, plus R5 continuous insulation. So that's going to be like rigid foam on the outside or something like that. R13 plus 10 would be R13 cavity, so probably a 2x4 wall, and R10 continuous. And then finally, there's a 0 plus 15, which means nothing in the cavity, and a 15, R15 continuous insulation. So those are the different options, and that's what that 20 plus 5 means. It means cavity plus continuous. Now, I could not do a R, in this case, let's say an R21 plus 4, because that R5 continuous insulation is worth more on the outside because it's uninterrupted by framing. So I can't trade off in an exactly additive way. It doesn't mean just a total of R25. Within the cavity, I can add and subtract, but I can't trade it off against continuous insulation in this table. There's whole building UA that I can use, but the table is giving me an amount of insulation in specific places, and they have to be in those specific places in order to use this table for compliance. The mass wall, 8 or 13, the 8 means more than half, or I'm sorry, 50% or more of the insulation is to the exterior of that mass wall. The 13 in this case means more than half is to the interior. So R8, if 50% or more is to the exterior, R13, if more than 50% is to the interior. That's how the mass wall cell works there in the table. Floor value is R19. That's for floors over unconditioned space. Basement wall R value, if we're conditioning the basement, in climate zone 3, we have a 5/13. In this case, the 5 means continuous and the 13 means cavity. So even though it looks similar to that mass wall, it doesn't mean the same thing in the table. The 5 is continuous, the 13 is cavity. And that's an either or, it's not additive like in the wall section. So it's important to look at the footnotes if you're unsure of what these things mean in the table. And then finally, there's a slab edge insulation requirement for the first time in climate zone 3 in 2021 IECC. And that's an R10 slab edge insulation. It has to come to the top of the slab edge, and then it has to go 2 feet, and it can go 2 feet down and out, 2 feet down and in, 2 feet. There's a lot of different ways it can be installed, and we'll talk more about that in module 5, but it does have to go a total linear distance of 2 feet and be R10 in value.
No, can it be interior or exterior?
It can, as long as it comes to the top of the slab edge. So
Yeah.
if you're interior, then you have to detail around that slab edge. You can't, often you'll just have like 2 feet down from the bottom of the slab edge. Well, that's not stopping any heat transfer because you have a direct thermal path across.
Right. Thank you.
And then finally, we probably do have some condition crawls going in climate zone 3. There's R5 or 13. That does mean the same as the basement. And in condition crawl, it's unvented and sealed up. We don't insulate the floor of the space above. Instead, we insulate the walls. And in this case, it would be R5 continuous or R13 cavity insulation if you're putting stud cavities in the wall. There's also a U factor table. If none of these R value assemblies works for you, and you have maybe a different approach, maybe you have advanced framing, lower framing factor, maybe you have a different kind of wall assembly like a SIP wall, structural insulated panel, or an ICF, insulated concrete form, it's possible that your U factor will look better than the R value, because especially if it's a continuous insulation and uninterrupted by framing, that U factor might actually look better. And so you can use those U factor tables. This is also important when you look at that R49, because I know that's a little bit of a shock when the attic insulation changes. And so pay attention to the U factor, because that's going to be what you're going to need if you do a whole building UA and want to trade that off if it's difficult for you for some other part of the insulation or window in the building envelope. For climate zone 3A, so just the humid climate zone, there is no basement wall insulation R value and a 0.360 U factor. So again, we see 513 here for basement walls. That's only in the dry and in the marine climates. In 3A, this becomes not required in the code, and the U factor will match what you will see for other climate zones where there's no basement wall R value. In fact, it's 0.360, I believe, is the correct R value. So I think I've got an example of that later where it's not required, but I might not. So check that footnote because that does define what your U value will be there. For climate zone 4, 4A and 4B, this is not marine, so humid or dry. There have also been a number of stringency changes. We haven't seen anything since 2012, but now in 2021, there are a number of jumps in stringency. For sealing R value, the R value target is now R60 in the code. And that, I'm sure, is catching a lot of your attention. That's much more insulation than you're used to doing if you're building in climate zone 4. And so that's a big change. And pay attention as I talk a little bit more about the flexibility around that as we go. The wood frame wall R values will look the same as climate zone 3. You see 20 plus 5, 13 plus 10, or 0 plus 15. All of those are options. Mass wall is also the same, as well as floor R value. Basement wall R value is more stringent than in climate zone 3. It's a 10, 13, so that's 10 continuous or 13 cavity. And then finally, we have a sort of a change in stringency. It's the same R value of R10, it's slab edge, but the new linear distance of that insulation is 4 feet in climate zone 4, where it used to be 2 feet. So that's a change there in the linear distance of that insulation. And then finally, crawl spaces are a R10 continuous or R13 cavity insulation. Now you look at the U value here. Again, if you've got a different kind of a wall, you might be able to use these U value tables instead of the R value tables if none of the options there work for you. And I want to call this out here. Our 2021 IECC for the ceiling R value, a 0.024 U factor. You'll notice that that's only very slightly lower than the 0.026 given for a R49. So for R11 more insulation, you're only getting an incremental, a small change in the U factor target for that attic. And I think you'll find that the UA calculation favors being able to be flexible on the attic insulation by making some small changes in the building envelope, if that R60 is a problem for you. I know some builders who do R60 already, but that is a change for what the majority of builders are doing in climate zone 4 now. Climate zone 5 and 4C, so that's for marine. So all of climate zone 5 and then 4C has the following requirements. We have an R60 in the attic in 2021. Again, you'll see most of the changes here are in 2021. Same requirements as climate zones 4 and 3 for the walls, 20 plus 5, 13 plus 10, or 0 plus 15. There's an R13 or 17 mass wall. So that's 13 if more insulation is to the outside, 17 if more is to the inside. R30 for floors over unconditioned space. Basements has this option now. So it's 15 or 19 in climate zone 5. And that's again, a continuous or cavity. Or you can do a 13 plus 5, which means 13 cavity plus 5 continuous in the basement. So that's a little confusing, because the 15/19 is an either or, but then there's this other option where it's both and. So keep in mind that that option is there. It's not really a change in stringency. It's just another option described in the tables. And then also in the slab, that 4 foot is a new linear distance for the slab edge insulation for the same R10. Crawl space, conditioned crawl space walls, is still a 15 or 19 on the wall, or that 13 plus 5, that same option that's available for the basements. The U factor table is again available, and it's important to note again where you may or may not be able to trade off if you're using those U factors using a different type of wall. One thing I'll point out here in all of these slides that have this gray highlighting in 2015 for the wood frame wall U value, that should say U value in this table, not R value, but the U value there changes from a 0.57 to a 0.60, not because we had a change in the required R value, but because there was a code change that successfully argued that the correct U value for an R20 or 13 plus 5 should be a 0.060, not a 0.057. So it didn't really change the amount of insulation we have to have. It gave a different U value credit for that amount of insulation.
So Joe, what they argued there was a wood frame wall U value is somewhat less effective than was previously thought.
That was the argument, or that it was calculated incorrectly.
Okay.
Now, who was right on that? That's not really how the code works. But it was successful. So that's now the U factor that the code credits for that wall.
Got it. Thank you.
A couple of things on mass walls. We talked about them briefly. Climate zone 3, 4, and 5 all have different U factors if the mass wall, if more of the insulation is to the interior. So you see up here, we have that 13-17 split, for example, in climate zone 5. The 13 is what you're seeing here for a 0.082 U factor. But the code has in a footnote the U factor you're supposed to use in a situation where you have more of the insulation on the inside.
And Joe, can you just describe a typical mass wall for the audience?
Yeah, that could be anything from a timber frame wall to a brick wall that's not veneer, to a masonry block, to a poured concrete, to an ICF wall. And I think the ICF wall has a lot of potential for giving you flexibility in your code compliance, because the U factor you'll get, even in the colder climates, is going to be way better than they're giving you credit for with this 13-17. In fact, a lot of ICFs I've seen are like a 20-22 R value that's continuous. So your U value is going to perform really well compared to the code tables, and you'll have some added flexibility in what you want to do in your other envelope components. But
and the difference here, Joe, is that mass wall would be above ground assembly and basement wall is below ground assembly.
That's correct. So even though it's made of the same thing, your concrete block wall below ground is a basement wall, and you're at R15-19. Your above ground wall, if it's made of a product that has thermal mass, then you'll have this different requirement, or this different target. And the code lists a number of things. There's kind of this, I don't know, dozen items that are on that list. And if you do watch module 2, I actually list them there because it's more common to see mass walls in the South. But then you have there's also an equation where you can calculate the thermal mass of the material and demonstrate that it's a mass wall if it's not on that list.
Great, thank you.
There are a couple of ways that the code also allows some flexibility with what you see in the tables. So one of the major ways you'll see that is in a raised steel truss in the attic. So formerly, all three of these climates were using lower attic insulation levels. The climate zone 3 moved from a 38 to a 49, and 4 and 5 moved from a 49 to an R60. And the code allows some flexibility there. So let's say climate zone 3 for this example. If R49 is what the code requires, it also says that if I install a raised heel truss, so that's a higher heel at the truss, I can get more insulation uncompressed. And I want to keep that insulation uncompressed because as I compress it, it loses some of its R value. And I'll talk more about that in module 5. But the code says if I can keep an R38 uncompressed all the way across the attic and over the top plate at the eave, then I can use an R38 instead of an R49 and still use that R value table. I don't have to use some sort of trade-off to do that. So keep that in mind. And in climate zones 4 and 5, I can go from an R60 to an R49 if I have a raised heel truss and I can get my R49 all the way across that on top of the top plate at the eave and across the attic at an R49. And you'll need a different raised heel truss, obviously, for that R49 than you would for the R38. Here's a picture of one. And again, the code works R60 to R49, R49 to R38, and R38 to R30 for that trade-off or that flexibility. So with that raised heel truss, you get a better overall performance in the attic because you don't have compression. If you're using a standard truss, the code is assuming by the U value it gives you that you're getting significant compression at the eaves. So the R value, the R60 is going to be pretty compressed at the eaves if you're not using it. And what that's going to do is it's going to cause some performance issues there at the eave where you can't get full height insulation, which is why the code incentivizes that raised heel truss by allowing a lower amount of insulation. One other area where we have some flexibility on attics is attics without ceilings without attic spaces, excuse me. This applies to only part of the ceiling, but you can go down to an R30. So in this case, I'm giving an example of in climate zone 3, but I could go down to an R30 and in that space without an attic, that's the insulation requirement I have. I can't do it for the full roof. It's 500 square feet, 20% of roof area, whichever is less. So if part of your house has a vaulted ceiling, this might work. It also might work well for an addition where you're adding on sort of a bump out addition or something like that, where maybe the slope of the roof isn't going to allow the total insulation amount. If that addition's small enough, you might be under the size limit here compared to the whole house and be able to do that.
Joe, you could use this if you were using an HVAC chase in your trusses as well, right? To keep your HVAC inside the conditioned envelope.
That would be,
I mean, as long as it's 500 square feet or less.
I mean, if it's in an attic, I don't think that would apply. I think that you would need more. This is specifically if you don't have an attic space.
Okay. I see. Ceilings without attic spaces.
Yes.
Got it. Okay, thank you. So more cathedral type, yeah.
That's right. Good question, though. So now I've talked about what the code requires in the tables. Now I'm going to talk a little bit about how to do a UA calculation. This is actually how a lot of builders comply with the code. It might not be familiar with you if you don't do code compliance, familiar to you, but it is a good option if you want flexibility in your code compliance. So a UA calculation is just an area weighted average of the U value for the building envelope, and it's insulation and windows. So you can be trading across assemblies as long as the whole building envelope meets the target U factor. And I'm just going to show you how this works. It's very simple. Most people are going to use ResCheck or one of the energy modeling tools, which will also run a UA calculation. So almost nobody does this by hand, but I'm showing you this because it is possible to do it by hand if you don't have access to one of those tools. So for windows, if my required U value in climate zone 4 is 0.30 for the window, and I have 180 square feet of windows in the house, then my UA allowance is 54 for that assembly. Now, it doesn't matter that it's for that assembly, but I'm just going to add up all my assemblies at the end, and that's going to give me my total. For above grade walls, if I'm putting in that R20 plus 5 is now the climate zone 4 requirement, and I have 2,600 square feet of above grade walls, then I've got a UA allowance of 117. condition crawl space, which happens a fair amount in climate zone 4, especially on the coast. You might see a 0.065 would be the required U value for that, I think it's 1013 in the crawl space wall. So it's a 520 UA allowance, or excuse me, a 33.8 UA allowance for a 520 square foot crawl space. That's assuming a 4-foot crawl. And ceiling, I've got to get to that 0.24 for the 0.024 for the R60. I've got 1,000 square feet of attic space. And so that means I need a UA allowance of 24. I add all those up. This is simple multiplication. U value required times the area of my actual assembly that I'm proposing, and I get my UA allowance. So then if I want to then compare and change some things around for my building, I've just got to be equal to or less than that UA, because lower is less conductivity. So lower is better in this case. So let's say I go with a better window, 0.27. It's a pretty good window, Energy Star level in that climate zone. So 0.27 window. And now I've got a proposed UA for my windows of 0.48, 48.6. I'm going to go with the same wall that the code requires, the 20 plus 5, and I've got a 117. Again, the same thing in my crawl space. I'm not going to change that at all. And I've got a 33.8. But then with my attic, I'm going to go back to the R49 that I used to be able to do in the previous code. And now I've got a U value of 26. And you can see that I'm compliant by a few points there. I'm lower than the required UA or the UA allowance. So just by going to a slightly better window than the 0.30, I was able to go from a R60 to an R49 in the attic and still comply from a UA point of view. So the point here is that I'm still getting the same overall robustness of my envelope, but I'm going to find the assembly values that work best for me and how I build, and I can still comply that way. Again, almost none of you are ever going to have to do this by hand, but it is possible. Most people will use ResCheck. It's a free tool from DOE online. Okay, we've got about 12 minutes left in this class, and we're back to some questions about insulation here. So if you're still participating here live, you can answer these questions. The question here, first question here is, the goal of the R value requirements in the energy code is to stop what type of heat movement? Convective heat movement, conductive heat movement, radiant heat movement, or inductive heat movement? Okay, you're going to give it just a moment longer here. Okay, everybody got that right. Conductive heat movement is correct. We're trying to stop heat conducting across the building envelope, which is why R value resistivity is used. Next question, a basement wall insulation requirement of 15/19 means what in the code? Okay. R15 continuous or R19 cavity insulation. That is correct. We did have one answer, it looks like, for R15 interior or R19 exterior foundation insulation. That's not the right answer. So the R15 means continuous. The R19 means cavity insulation. So for a basement, that would mean I've framed out the basement walls, finished the basement, and I've got cavity insulation there for the R19. Next question, true or false, a manufacturer can claim additional R value for an insulating product that also air seals. True or false? Just a moment more here. Okay, we got about a 50-50 split. You cannot claim additional R value because of air sealing properties. So the R value, that labeled R value, is the amount of R value that's been tested according to FTC rules, and they can only label that R value and sell it in this country if it's tested according to those FTC rules. Sometimes you'll hear claims like, my product air seals and therefore it has a higher R value, and that's not true. It is doing two jobs at once, which is positive, but it's not correct to claim that it gives you a higher R value. So that's something to remember. R value is only measuring resistivity to heat conduction. True or false? I think this is the last question here. In an above grade wall, if the code requires R13 plus 5, I can install R18 cavity insulation and still comply using the prescriptive R value tables in the code. Give it just a minute longer here to pick your true or false. The answer is false if I'm using the prescriptive R value tables. Again, you can do a whole building UA, you could do the performance path, and then maybe use that R18. I'm not sure what that looks like, but the R13 plus 5 is not additive. It's a insulation in a specific spot, and it looks like everybody got the right answer, so that's great. Now with the remaining time, and again, think up your questions if you've got any before the end here. I'm going to just walk through a few examples of different type of insulation that innovative builders around the country are using. And these all are primarily coming from the US DOE's Tour of Zero. So this is a home that's using, I believe it's open cell spray foam in both their walls and their attic assembly. And this is more of a, it's an unvetted attic assembly as opposed to an assembly that's insulated at the bottom core of the truss. This is an example of half of a flash and bat system. So they've done an initial spray foam of a minimal thickness that gives air sealing and some R value. And then they're going to add bat insulation, fiberglass, mineral wool, something like that, to the assembly. And so in this case, they're kind of trying to use, they're combining materials for multiple reasons. They're getting some kind of value optimization out of it, and then they're also getting the added air sealing benefit of the insulation there. This is a rigid foam on the exterior. All the joints and seams are taped, and that's as it should be. And this is creating a thermal break across those studs, so that the studs, which are more conductive than the insulation, are not interrupting the insulation, and the insulation is stopping that heat transfer on the outside. There's another example of a continuous insulation. This is a product that's also structural in nature. So it's a structural sheathing with an insulated component to it. And again, that's to the exterior. This is often going to be combined with insulation in the cavity as well, both of these examples. This is a picture of a double wall. You'll see here, these are two 2x4 walls with a gap in between, and this wall will be filled with insulation, with blown in usually. So that means that the gap in between those two walls will be filled with insulation and will essentially be creating a continuous insulation barrier or layer in between those two filled 2x4 walls. Another picture of the double wall there. This is a structural insulated panel, or SIP, and that's where there's a rigid foam in between two structural sheathing components, and the structural components are sometimes plywood, they're OSB, they're magnesium oxide. There's a bunch of different types of SIPs, and there's different foams that go in the middle of them. So they'll have different R values, and you'll need to know what those insulation, what that insulation has as an R value for inch to be able to calculate it. You're also likely to be able to use this product to comply with the U factor tables because it is a continuous product. Another picture of a part of a SIP system. This is blown-in insulation. And the nice thing about blown-in insulation is it conforms to the cavity. So if you have a narrow cavity, if you've got plumbing and wiring and electrical boxes, it's going to fill around that, and you don't have to do a lot of cutting of your insulation and that sort of thing. This is an insulated concrete form. So it's two panels of rigid foam insulation, and concrete is poured into that as it's assembled in order to create a very strong and very airtight assembly. Here's a block of this, and it's usually built block by block on site and then poured so that it doesn't come obviously filled with concrete, which is very heavy. And then finally, this is another spray foam assembly. This one is in somewhere in Minnesota, I believe. And here they've sprayed both the wall and the attic again with spray foam. So that concludes our discussion today, but I am happy to answer any final questions you might have in these last few minutes.
Joe, the one question that came up was, and it's maybe a little bit off, but the air leakage requirements for windows at 0.3 cubic feet per minute per square foot, right? Mm. How do we think about that in terms of impacting your blower door test? Is it more stringent or less stringent at 50 pascals? What kind of, do you have any data around that?
It's not, you can't compare stringency on that because the ACH 50 target is a volume-based target.
Right.
Whereas the window is measuring a surface area. Mm-hmm. So it's probably more appropriate to compare it against the compartmentalization measurement, which is surface area. Okay. And in that case, it's just about right in line with code on that measurement.
I guess my question is it in line with 3 ACH 50 or what is it in line with?
It's meaningless compared to 3 ACH 50, but it is in line with, if you're doing a compartmentalization test, which is allowed in the 2021 code, and we'll talk about that in module 6. It is in line with that code target, but it is something that's tested in the factory, and it's leakage through the window unit itself.
Right. Awesome. Great. Well, Joe, I want to thank you. And just a reminder, if you've just completed this course, you'll want to click ahead to module 5 in our series. And we look forward to seeing everybody in that next module.
Okay. Thanks so much.
Thanks, Joe.